Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 9, Lesson 7 on tangent, secant, proofs, and practice. All right, so I call it proofs and practice because what we're going to be doing in the lesson is we're just going to be proving the theorems that we saw in lesson number 6 that involve the angles that tangents and secants made, as well as chords and tangents. The practice piece is really on the homework, where you will do a little bit of the proof, but mostly you'll just be practicing with those theorems. So let's get right into it and see what we can prove. Now, first, I want to talk about the word derivations. All right, in this lesson, we will prove the angle-arc relationships that we saw in the last lesson that involve tangents, secants, and chords. These types of proofs will rely on algebraic principles rather than the more formal geometric proofs that we've seen, you know, the T-table proofs with all the statements and reasons and stuff. These types of proofs are generally called derivations, and you see them all the time in the areas of physics and engineering when they derive formulas that they come up with. And that's kind of like we had these formulas, right? The measure of this angle is the measure of this arc minus the measure of that arc divided by 2, you know, things like that, right? That's really kind of a formula, right? But we want to see and prove where that comes from. Now, let's start though by proving the angle formed by a tangent and a chord in exercise number 1. In the diagram of circle O shown, BE is tangent to the circle at A. Diameter AOD has been drawn as well as chord AC. We wish to prove that the measure of angle BAC is 1/2 the measure of arc AC. So let's pause just for a moment and talk about this, right? In the last lesson, we had this theorem that said that if you have a tangent and if you have a chord, then the arc that is created, or the arc that is intercepted by that chord and that tangent, right, that angle will be 1/2 the measure of that arc. But we didn't prove it, right? The measure of angle BAC is 1/2 the measure of arc AC. All right, in this problem, we're going to prove that. But I'm going to kind of walk you through the pieces of the proof until we get to the end, and then we're going to really just kind of go through it. So let's take a look at letter A. What is the measure of angle BAD? How do we know? All right, well, pause the video now and at least see if you can answer what is the measure of angle BAD. Well, the measure of angle BAD is going to be 90 degrees. All right, and that's because all tangents are perpendicular to radii at the point of tangency. All right, so I know going into this proof that that is a 90-degree angle, and that's going to be part of it. All right, so now let's take a look at letter B. What is the measure of angle CAD in terms of the arc it intercepts? Write down the relationship. All right, well, go ahead and do that. Write down the relationship between the measure of angle CAD, which you're going to have to locate on the diagram, and the measure of the arc that it intercepts. All right, well, it's simple enough, right? The measure of angle CAD, which is this, is going to be 1/2 of the measure of the arc that it intercepts. So that I'm not writing in highlighter, right? We know that the measure of angle CAD is going to be 1/2 the measure of arc CD. And we proved that, right? That's the inscribed angle theorem in a circle. And we proved that a few lessons ago, right? Now let's take a look at letter C. Fill in the missing angles and arcs using the whole is the sum of its parts. All right, so what I'd like you to do is I'd like you to fill in both of these two things as best as you can. Pause the video now. All right, well, this one says the measure of angle BAC plus the measure of angle CAD is equal to what? Well, the measure of BAC plus the measure of CAD, those are adjacent angles, and so we can just sum them, and we can say those are all equal to the measure of angle BAD, right? And I'm going to go even further and say that's equal to 90 degrees. Okay, simple enough. Now, the measure of arc AC, right, plus the measure of arc CD has got to be the measure of arc AD, right? And just to be very clear, the measure of arc AD is 180 degrees. Okay? And that's all we're going to really now need to prove our theorem. So let's get into it. Letter D. Now use A, B, and C to prove that the measure of arc BAC, the measure of angle BAC is equal to 1/2 the measure of arc AC. So again, I want you to really be keeping in mind, keep your eye on the ball. What I want to now prove is that the measure of this angle, right, is going to be 1/2 the measure of this arc. That's what I'm going with, all right? So let's get it done, okay? So the first thing I'm going to do is just state, right, the following. The measure of angle BAC is equal to the measure of angle BAD minus the measure of angle CAD. All right, let's just make sure you have that, right? So the angle I'm really trying to prove something about, BAC, I'm going to say is the measure of angle BAD minus the measure of angle CAD. And really all I'm stating here is this relationship, except I've solved it for the measure of angle BAC, right? Just BAD minus CAD. Now, my next line down, I'm going to do a double substitution. I'm going to substitute something for BAD, and I'm going to substitute something for angle CAD. In fact, what I'm going to say is that the measure of angle BAC is equal to 90 degrees, because I know that's the measure of angle BAD, minus 1/2 the measure of arc CD, right? So I know the measure of angle BAD is that 90-degree angle, and I know that CAD is 1/2 the measure of arc CD. Simple enough. Now, I'm going to put something in for the measure of arc CD. You see, I can say that the measure of arc CD is the measure of arc AD minus the measure of arc AC. And again, that's just using the whole as the sum of its parts, right? But I'm just taking the whole, which is AD, and I'm subtracting off AC, right? And that should have given me the measure of arc CD. Let's do another substitution. We know that the measure of arc AD is 180 degrees, right? Because that is a semicircular arc. So I can now say the measure of angle BAC is equal to 90 degrees minus 1/2 of 180 degrees minus the measure of arc AC. Now, before we move on and really effectively finish out our proof, always keep in mind what you're trying to prove, right? I'm trying to prove that the measure of angle BAC is equal to 1/2 times the measure of arc AC. And look, I've got my 1/2, I've got my arc AC, so I'm getting close, right? I'm getting very close. And some of you probably already see where we're going to go with this. I am now going to distribute a multiplication by negative 1/2 through that parentheses. Now, what do I get when I do that? Well, I get the measure of arc BAC is equal to 90 minus 1/2 times 180 plus 1/2 times the measure of arc AC. I can't leave that with the red. This is too good of a proof right now. Now, keep in mind, right, why do I have a plus 1/2 the measure of arc AC here? Because I have a negative 1/2 times a negative 1 measure of AC. So that negative times a negative becomes that positive. All right, we're just about there, right? The measure of angle BAC is equal to 90 degrees. 1/2 times 180 is 90 degrees plus 1/2 the measure of arc AC. And keep in mind, right, that subtraction was already distributed through up here. There's no subtraction now attached to that. I can now say 90 minus 90 is gone, and the measure of angle BAC is 1/2 the measure of arc AC. And on a proof like that, we have to finish it by saying QED. All right? Maybe not the inventor of geometry, but almost one of the founding members of geometry was, right, this guy named Euclid. And he would end all of his proofs with QED, which was Latin for quod erat demonstratum, literally translated that which was to be proven. In other words, we set out to prove that the measure of angle BAC was equal to 1/2 the measure of arc AC, and that's exactly what we showed. So you kind of throw that one in just to go, yeah, I did it, right? Anyway, there it is. That is why we can say that the measure of an angle formed by a tangent and a chord, right, will be 1/2 of the measure of the arc that it intercepts. We've got some more proof to do. Let's keep going. Now let's take a look at the angle formed by two secants. All right, and this one's kind of cool. It won't be nearly as algebraically intensive, but it will bring in some nice stuff that we've seen previously in this course. Let's take a look. The angle formed by two secants. In circle O, secants PC and PD have been drawn from exterior point P. We want to prove that the measure of angle P is equal to 1/2 the measure of arc CD minus the measure of arc AB. Auxiliary line segment AD has been drawn, dashed, to aid in this proof. All right, so we've drawn these auxiliary lines many times before, right? You know, if we're normally doing a problem like this, right, that line's not even drawn in there, but it's going to be drawn in to help us with this proof. So let's take a look at letter A. Using the exterior angle theorem, fill in the following. The measure of angle CAD is equal to the measure of angle P plus what angle? All right, pause the video now and see if you can write down the correct angle here. All right, now this is really key. The exterior angle theorem is really important, right? Angle CAD, right, is an exterior angle to this triangle, right? And we've got this theorem that says any exterior angle will always be the sum of the two remote interior angles. Angle P is one of them, and angle D is the other one. Now I can either call that angle ADB or I can just call it angle D. It's okay to call it angle D because there is no other angle D that it could possibly be confused with. All right? So the measure of angle CAD is equal to the measure of angle P plus the measure of angle D. Exterior angle theorem. All right, let's take a look at letter B. Solve the equation for the measure of angle P. Well, this is pretty easy, right? All I would have to do is subtract a measure of angle D from both sides, and the measure of angle P will simply be the measure of angle CAD minus the measure of angle D. Okay, that's all. You know, just the measure of angle P, which is the one that I'm going for, right, is equal to the measure of angle CAD, which is that exterior angle, minus the measure of that one remote interior angle. Simple enough. And now let's finish off the proof, which is actually going to be quite easy. Letter C. Use your answer to B along with the inscribed angle theorem to derive the fact that the measure of angle P is 1/2 the measure of arc CD minus the measure of arc AB. All right, well, my first line is actually this line, so I'm just going to move this right down here. Okay, no need for me to write it down again, but look at how easy this is going to be now, right? The measure of angle CAD. Well, the measure of angle CAD, right, is that angle, and that's of course an inscribed angle, and the, whoops, and the arc that it intercepts is that arc, right? Likewise, if I've got this measure of angle D, let me get here, right? That's this angle, and that is going to intercept, whoops, that's going to intercept that arc. All right? So I can now say that the measure of angle P is going to be 1/2 the measure of arc CD minus 1/2 the measure of arc AB. All right, keep in mind what we're trying to prove. The measure of angle P is 1/2 of the difference between the measure of CD and the measure of AB. So I'm just going to factor a 1/2 out of each one of those, and I'll get 1/2 times the measure of arc CD minus the measure of arc AB. I'm not sure that that proof actually even deserves a QED, but I'm writing it down anyway. How nice is that, right? We use the exterior angle theorem along with an auxiliary line, right, to establish that that exterior angle, which is one of the two remote interior angles for that one, is simply going to be that angle minus that angle. But both of those two angles are inscribed angles, and therefore we can just substitute in for them 1/2 of their intercepted arcs, and that's where that subtraction comes from, right? The subtraction really comes from the fact that one of those angles is an exterior angle, which means it must be the sum of those two angles, and then we just rearrange it to get our desired result. All right, let's do one more proof. Here's our last one. Whoops, wow, we're just skipping over that one. All right, here's our last one. The angle formed by a secant and a tangent. Let's take a look. Angle formed by a secant and a tangent. In the diagram below of circle O, tangent PE and secant PD have been drawn from exterior point P. We want to prove that the measure of angle P is 1/2 the measure of arc BCD minus the measure of arc AB. Auxiliary line segment BD has been drawn to aid in the proof. All right, this is going to seem very, very similar to the last proof, all right, with one minor difference. But let's take a look at letter A. Using the exterior angle theorem, fill in the following. The measure of angle EBD equals the measure of angle P plus what? Pause the video now and fill in that blank. Well, again, right, we've got this triangle, BPD or DBP or however you want to say it, right? Exterior angle EBD is right here, okay? That angle, right, has two remote interior angles, angle P and angle D. So the measure of angle EBD is the measure of angle P plus the measure of angle D. Simple enough. Now, just like before, letter B, solve the above equation for the measure of angle P. All right, why don't you go ahead and do that? That should be quick. All right, let's do it. Again, same thing. All we have to do is just move the measure of angle D over to the other side. So the measure of angle P is the measure of angle EBD minus the measure of angle D. And now we're pretty much there. Just like before, we want to now finish this thing off by taking this thing down here and using it to start the proof. Letter C. Use both the inscribed angle theorem and the tangent chord angle theorem to show that the measure of angle P is equal to 1/2 the measure of arc BCD minus arc AB. All right, well, yeah, we're basically just filling those blanks in, right? EBD now, this angle, right, is an angle that is formed by this tangent and this chord. And literally what we did in the first exercise was prove that that particular angle will be 1/2 of the arc that it intercepts. So it's intercepting the arc BCD. So this is going to be 1/2 the measure of arc BCD, right? Minus now, of course, angle D is an inscribed angle and it's intercepting arc AB. So that's just going to be 1/2 the measure of arc AB. And now I can factor the 1/2 out of both sides, and the measure of angle P is 1/2 the measure of arc BCD minus the measure of arc AB. Easy peasy, right? Simple as all simple gets. Okay, I won't even put a QED down because it's essentially the same proof as the one that we just did in exercise number 2. So it doesn't seem to warrant it. Now, we never really want to use something in geometry if we can help it without proving it. In the last lesson, we introduced all of the theorems that we proved today, and in this lesson we ended up proving them. In fact, the Common Core standards and the Next Generation standards state that students should be able to prove theorems that involve chords, secants, and tangents in a circle and then use them to solve problems. Now, we kind of did that in the opposite order in this case, in that in Lesson 6 we introduced the theorems and you used them to solve problems. In this particular lesson, we actually proved those theorems. Whether or not you would have to do that on a state exam is more of a question, but you could have to do some kind of a proof that was similar to what we just did. All right, well, we're going to be moving on from that and doing additional problems in the next lesson that kind of have some of this involved in it. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.